Okay, we are supposed to start from memory management, but I remember we had already tackled process management.
Yeah.
And if you look at what we did on process management, I remember we said processes are executable, or those are executable statements which we are supposed to execute, but we must be able to store them somewhere that you can use maybe within the timeline or maybe in future. So for this case, that's why we said when you look at process management, we said we need to have a fast execution of processes. And if you can remember on that, that is where we say we need to look at performance criteria. And one of them was throughput, turnaround time. Then we talked about waiting time, where we said you're talking about turnaround time is the time that you take for a process to execute, where throughput is the number of time processes that are supposed to be executed within a given minute or time. So within that, we did some calculations, and most of these calculations we used some algorithms, and one of the algorithms that we used was round robin, first come first serve, shortest
first come first serve.
Okay, and I think for now you understand them. And the basic concept on that was to introduce to us on memory management and what we should use within the memory management. And that is why I want us, today we start on memory management, and so that we can be able to understand why we were having a process. So if you look at memory management, we start with the memory. And I think memory is not new to you, because when you talk about memory, we always look at memory as a storage or as a container that is mostly used to store some information. But when you're storing this information, sometimes it can be lost. That's why we need to have management. And when you look at memory management, this is when you're looking at now controlling the access, organizing the memory, the processes in a memory, and how processes are supposed to be executed and shared to users. So the function or the element that does this is the operating system, and operating system assists the users or the memories to be allocated the way they are supposed to be allocated. So if you understand about now the function or the activities of an operating system in memory management is to activate the memory, deactivate the memory, and keep track of the memories. When you talk about activation, remember that the moment you are trying to execute a process in the memory, we must be able to look at now activation on how processes are supposed to be executed. So that is what we will be looking at, activation and deactivation of the process. Keeping track which memory has been used and which memory has not been used, so that we can use it. So we will not be having some process loss or memory loss within the execution. And for this case, we will look at the overview of what we will cover within the memory management. And that is part of what we will cover, activities. Then we look at now types of memories. We know that we have primary memory, we have secondary memory, and many other memories that we have. But the moment we are storing these processes in a memory, we always look at an issues of processes loss or inactive memories, which can result to some issues when you're allocating a process in a memory. So for this case, that's why we need to work with what we call memory management technique. And one of the techniques that we'll be discussing is what we call paging. Then the next one that we'll be discussing is what we call segmentation. Then the next one is partitioning and the virtual memory. So for that, we still look at now, when you are allocating a process in the memory or maybe an activity in the memory, you need to use some algorithms. One of them is utmost algorithm, least frequently used memory algorithm, first come, first serve memory algorithm, which can assist us to allocate the memory or to process where they are supposed to be allocated in a memory. Remember, these memories, sometimes they are not even active, so you must activate them so that they can be used. Then after that, will be facilitated through by what you call the placement algorithms. And these placement algorithms or policies, sometimes we call them placement policy. We have best fit, worst fit, first and next fit, and many others that you still be able to discuss. So after we understand that, we can be able to understand about the memory organization. And this is where we understand about the function of memory organization. And we always look at hardware and software organization. So I think we can pause at that point. We can start. And I want us to share some notes here, of which I have sent these notes. And we try to understand about this memory. And if you look at the notes that I have shared, we are saying memory management is a functionality of an operating system which handles or manages primary memory. Now, when you talk about primary memory, what are we talking about? In most cases, we are talking about a RAM. Mostly, we are talking about a ROM as a memory. And that's why if you look at now, maybe if I can be able to share using a paint somewhere, we always look at a memory which is always presented in a manner that it's like a pyramid that has been presented on this. And if I can use a very simple diagram, we have like something like a memory here, where we can have maybe we have the primary memory. We start with the cache memory. We have registers, and then we have primary memory, and then we have the secondary memory. And the moment we have these memories, of which we have others, like we have the holographic memory, we have bubble memory, and many others. But let us first of all discuss about the cache memory. And when you talk about the cache memory, we always say that these are the memories that speed up the execution of the processes. So this cache memory, it is inside a primary memory, and this primary memory, it is inside a RAM. So when you talk about cache memory, it's inside a RAM. And it is speed up the execution of those slower devices. Like now, maybe a keyboard. A keyboard is very slow when you're executing jobs, and you find that now you cannot execute many jobs because it's very slow. So we need to use cache memory. When you're using registers, mostly they are used to store temporary jobs, and that's why sometimes you find that when you're using a hard disk, maybe you're not using a floppy disk. Where is it stored? This floppy disk is stored in a temporary memory, and that is now what you call a register. So you can call it anytime. So I think primary memory, you know it because I have explained the cache memory. So at the end of this, I want you to research on various types of cache memory or types of cache memory and configuration. Types of configuration of cache memory. Configuration cache memory. And the moment you talk about configuration memory, we talk about direct mapping. We have direct mapping. Then we have associative. We have associative memory. We have associative memory, and we have full associative memory. This question has not been examined for long, and I am expecting maybe we can have a question on this for those people who are sitting exam on July and maybe on December. Which are those types of cache configuration? And those types of cache configuration, we have direct mapping, associative memory, and full memory. So if you look at this pyramid, that is what you are looking at here, and we are saying it is mostly used to store, maybe to manage the primary memory. And when you're managing this primary memory, you can look at now, how will you be able to manage? That's why now we look at various functions. So we can look at various functions of the memory. on that. But before we go to that, if you look at most of the memory, they are organized in form of an array. And because they are organized in form of an array, there is where the operating system is supposed to sit, process 1, process 2, process 3, and maybe we have other empty memory somewhere. But if you can look at this, we always store different processes in different memory sections. So we cannot store two processes in the same memory. So we have to store it in a separate memory. That's why we have already given the separate allocation of this memory. And the function, or maybe the instructions and data to memory addresses can be done by the following ways. So anything that you store within these memories or processes, it can either be done by these ways, either compiling time, loading time, or execution time. So the moment you are looking at compiling time, we look at now the moment you are generating an absolute code that can be used in binding data in the execution. And when you do that, you can be able now to relocate the code where it's supposed to be used for execution. That's why we have the execution time. So we compile, we take all the jobs, we generate the absolute code that can be used for execution. We combine those cons together. It's like you're combining A plus B plus C. Then after that, we execute those A plus B plus C, but we're executing it in a given memory. So for that case, memory try to work with various functions, either dynamic loading, dynamic linking. And the moment you talk about dynamic loading, this is where when the memory comes or when the process comes, it loads immediately. So if the memory is empty, automatically it loads immediately by linking some processes in the execution from either small to big fashion of execution. But when you are doing this, there is a memory interpretation that occurs within that, and it has to use some addressing. And this addressing, we'll be able to look at them the moment we'll be looking at memory techniques, because we have one of them is logical addressing, and the next one is what you call the physical addressing. Logical addressing is always virtual, and sometimes we call it virtual address, because the moment we call it virtual address, we are saying this is a memory that is within the CPU. When you talk about the physical addressing, we are now talking about the memory that is in a certain memory location, maybe a hard disk. So that memory that is in a hard disk is the one that we call physical memory addressing, because you can see it. Mostly, they always try to create some interpretation of the unit. So for this interpretation, I want us, first of all, to look at the functions of the memory. And mostly we look at the functions of an operating system or the activities of an operating system in memory management, so that now we can start from the memory allocation technique. Let's try to understand that when you look at memory management, the function of an operating system or the activities of an operating system is always to make sure that there is the activation of the memory and activation of the memory, and then keeping track of the memory when it is used and when it is supposed to be used. Because sometimes we cannot say that we are repeating a process at any time. We have to make sure that now when you are allocating a process, we have to allocate the process where it is supposed to be, because it is having an available memory through representation of those algorithms that we have talked about. Then we have to look at keeping track of the memory. When you keep track of the memory, now what we are looking at is we are asking ourselves, where is the process allocated? Then when it is allocated in that memory, is there any process that requires that memory? If there is a process that requires that memory, now we can say we can be able to do away with it. And maybe we can share other executable memories within that. But sometimes you can ask ourselves, how will you know that the memory is full and when we require a process? So sometimes we need to understand there are algorithms that are used, and those algorithms are assisted by the placement policies. And these placement policies are the ones that will be able to allow us to identify where the memory, the process is supposed to be stored, and which memory is supposed to be used at that point. That's why memory techniques intervened. And when you look at the memory techniques, mostly we are looking at where we have a memory that is empty, and this memory that is empty, maybe we can say this like something that is like an empty, because we say that a memory is like an array. But we must be able to look at now, how will you share this memory? How will you create these partitions here? How will you create this section? Because this is a section, this is another section, this is another section, this is another section. What are the determinants? So we are looking at the factors. And the moment you look at the factors, mostly we are looking at the size of the memory. Then we are looking at the type of the hardware. So we are looking at the type of the hardware, which type of the memory, because sometimes we find that now we have the memory, but we cannot clearly define it, because now in our case we have already said the memory is a hardware. Then we need to look at now which are the resources that you are supposed to use. And mostly when you're talking about the resources, we are talking about input-output resources, file resources, etc. So for this case, that's why we need to use what you call the memory techniques in order now to allow us to create a memory sections. And this memory section will be utilized by a process in the manner that will not create wastage of resources in them. So that's why one of the memory technique that we have is what you call partitioning. And I think partitioning is not new. And the moment you look at now partitioning, we are looking at now dividing the memory. It's like we are having a frame, and this frame is not allocated, but we ask ourselves, how will you divide this memory to this? There are those that you divide either very small. There are those that you divide as either very big memory. So for this case, in partitioning was a traditional method of memory allocation. And because it was a traditional method of memory allocation, we can say we create divisions. And when you create these divisions, you can see this division is not equal to this. This division is not equal to this. So it forms two types. It forms two types. One of the types that you form is what you call fixed memory allocation. And then the next one that we have is what you call dynamic memory allocation. So there are two types of partition, fixed partition and dynamic partition. When you look at fixed partitions, you classify them into two. And one classification is unequal. Then we have the next one, which is called equal. So we have unequal and we have equal. When we talk about equal, suppose we have a memory of 64 memories and you want to divide it. Either you can divide this memory either into equal parts. So you must be able to know how many sections will be created in this memory allocation that we are having here. So we come and divide them equally, meaning the first memory and the second memory has 4 maybe, the next one has 4, the next one has 4, and the next one has 4. But if you use an equal, it means we are having this frame, and this frame sometimes you find that this is 4 memory, this is 5, and this is 10. So until you exhaust 64 memory. So in this case, we can say we are not creating efficiency. And because we're not creating efficiency, it results to some issues of execution. That's why most of the memories, before I come to these, maybe we can look at what we are saying on partitioning. So if you look at the allocations, maybe before we even look at it, maybe I can still proceed and explain. So we are saying, if you look at this equal, sometimes you can have a process, and because you have a process 1, which has 4 memory, Then we have process 2, which has 2 memory. Then we have process 3, which has 10 memory. And because now we are using equal memory, remember here we are using 4 memory, here you are using 4 memory, here we are using another 4 memory, we are using another 4 memory, etc. Remember, this one we have already allocated for operating system. We have already allocated it for operating system. Suppose we are using the first come, first serve memory, because we are using some defined algorithm. If we are using first come, first serve algorithm, this memory, this process 1 will be the first one to be allocated in this first memory. So you allocate process 1 here. But the moment you allocate process 2, you allocate process 2 here. Remember, even if this memory is large enough, it cannot be used to hold process 2. Here, we have already utilized part of this 4, and we have utilized 2 memory. But the remaining now becomes what you call a whole. So we are now referring it to a whole. And because we are referring it to a whole, it becomes a waste memory. So that's why we are saying when you're using partitioning, sometimes we have wastage of memories. And for this case, when we are allocating this process, we are now assuming this process 1 has not even completed, but we have to allocate process 3. So we allocate process 3 here. So we are allocating part of process 3, where we are allocating only 4, but the remaining is now 6. The remaining is now 6. And because the remaining is now 6, we can now say that whatever has now remained here, it cannot be accommodated in this memory. So where will you store this part of 6? So this part of 6, we are now supposed to store it in a virtual memory, which we call an overlay memory. So we call it an overlay memory. And this overlay memory is the one that is mostly used to store it temporarily. So you are storing it temporarily so that now we can use it in a given time when you find that there is a certain portion of the memory that you can utilize. So we assume that this process has already executed. So when you do that, you find that this is now free. So you have free memory. Now you take part of it, which is 4, and then we allocate it here, where we are remaining with 2 in an overlay memory. So what we are saying is that the moment we are trying to allocate these processes, in this execution, you find that we have some memory loss. So we have losses. And these losses, one of them, we have what you call some process loss. And because we have some process loss, it results to 2 main problems. One of them is internal. We have internal, and the next one is what you call the external. This external, we call them what? External fragmentation. External fragmentation. So the moment we are calling them internal and external fragmentation, we are saying, if I can use a new page somewhere here, and we are assuming that now, whatever we have already allocated, let me use a very big one. So we have allocated process 1 here, process 2 here, but now we had already allocated part of that memory. We have not allocated all the memory. Then we have allocated another process 3 here, which is not even full. So it is waiting for this memory. So this memory that is left here, we have called it a whole. And because we are calling it a whole, the whole of this result to what you call internal. Internal. But now, because process 3 was not able to accommodate in this memory fully, there is a part of the memory which has been taken to an overlay. Now, it results to what you call an external memory. So how can you define an external memory? Internal and the external fragmentation. Internal fragmentation is when you find that the memory that you are trying to utilize is too big than the process itself. So the process has an allocation of the memory which is too small. So you find that it is not even accommodating. So here we have what you call the wastage memory, or the waste of the memory. Then the external fragmentation is when you find that the memory is too small than a process. So the process itself is too big because process 2 was having the text. So the process was too big to be accommodated in this memory, which now results to some issues on that. And in this case, the operating system has to do more of its functions by making sure that every execution that you're supposed to execute is adherent to. And for you to do that, we do what we call compaction. So there is what you call compaction. So compaction is a method of ensuring that wholes are brought together. So it's like we are having a memory here. So if process 1 has already completed, so we are having a memory of processes here, but we are left with a memory here, which can be utilized for another execution. Where now, these are the processes that are executing. So we can now leave the execution. So a compaction is a method of bringing the process together and the memories together to allow other processes to execute in that. But now, let us try to understand when you're using what we call a dynamic partitioning. Remember, we have talked about fixed partitioning, and we have said when you're using fixed partitioning, it is either we use equal or unequal partitions. And those equal or unequal partitions can result in internal fragmentation, or what we call the external fragmentation. But for this case now, we want to reduce, totally, we want to completely reduce what we call the external fragmentation. Because when you are having the external fragmentation, sometimes we are having them issues in the process execution. At the moment we are having some issues in process execution, we can resort to some errors in that execution. So the best way to solve these issues that you are having in internal fragmentations, or that you are having in a fixed fragmentation, is to always make sure that we have what you call dynamic memory. So the moment you are having dynamic memory, remembering that we have already talked about the fixed memory, so this is where you have a memory, but the memory that you are having here, and the process, we are assuming that process 1 had 4, the other one had 2, and the next one had 2. We now, first of all, allocate the memory for operating system. We allocate the memory for operating system. So the moment this process requires to be allocated the memory, we will allocate a memory in the time that you require it. So for this case, I will take 4, and I allocate 4 here for this process. Then the next one that is supposed to execute is 2. So we will have 2. The next one that I will allocate is now 10. We are now fixing the memory the way they are supposed to be fixed within that time. And for this case, we have totally reduced what you call the internal fragmentation. We have totally reduced the internal fragmentation. But what we cannot reduce totally is the external fragmentation. Why? We cannot reduce completely the external fragmentation because suppose this process, because it was the first one, it is now free. If this memory is now free, we are saying that this memory requires some process to execute it. Where we are using some algorithms. So you must use some algorithm. Then we must use some placement policy, because we are supposed to talk about replacement algorithm and placement policy. So replacement algorithm is what we call least frequently used or fast come fast serve. Placement policies, these are the guidelines, and this is where we have what you call the next fit, the last fit, and many others that we have. So for this case, because this one is now free, we still require compactioning. And if you can understand what we have talked about compactioning, we have said compaction is when you bring the process together and the memories together and the wholes together. So you need to pull these two up and this then up, then this you bring down, so that now if you have another process that is supposed to execute, now you can bring it to the end, which will allocate this. So in this case, if you try to interrelate those two, we have totally reduced the internal fragmentation. But what has not been totally reduced is the external fragmentation. And the only way that you can be able to reduce that is through what you call paging. So you can use paging. And because we have a diagram here, remember here now, we were talking about internal and external fragmentation. Well, we have said internal fragmentation here is the memory block assigned to a process bigger. Some portions of the memory is left unused, and it cannot be used by another process. That's why we have said if it is true for the other one, and it has left some memory portion somewhere here, it cannot be used. That is a waste. And I think that is very clear of that. External fragment, total space is enough to satisfy a request or to reside a process in it, but it is not contiguous. The meaning of the word contiguous is following each other. So it is not following each other. If you look at the first case, we were saying we are having a memory, but now we have already allocated process 3 here, but it was not pre-accommodation. So you can allocate it somewhere here. So it is not contiguously arranged. One is at the top, one is at the bottom. So it is not contiguously arranged. So in this case, you can only solve these issues that we have through what you call paging. And I want to explain paging, maybe using this page. Well, we can say the first thing that we require is what you call logical unrest and the physical unrest. And this logical unrest, we have said we are now referring to it as CPU. The other one is now maybe we are looking at maybe the hard disk or any other memory. Like maybe we can have maybe what? We can have maybe RAM, etc. We can have ROM, etc. And I think you know what are ROMs and what are RAMs. You have done that in ICT, where we say RAM is temporary and this is permanent. So in this case, we require an unrest. Let me use a very clear page here, where we require a logical unrest. And this logical unrest, you require a page and you require a displacement. If you can look at this, we are looking at a page and displacement. So in this case, we are looking at page number and a page offset. So a page number is used as an index into a page table, which contain page unrest of each page in first column. So we are looking at now, this is a page that has everything of a process. But this now, page offset, is the one that is now supposed to take the process to the physical memory. So for this case, because now we are using a CPU here, we remember we have a CPU somewhere here. We need to have pages. So we can allocate a page here, and here we can assume that we have what you call a physical memory. This one we have a logical memory. But now you have to allocate a process here, because now we have already defined a process, and we assume that the process 1 is supposed to be allocated, process 2 is supposed to be allocated, and process 3 is supposed to be allocated. And because these processes are supposed to be allocated, if there is another process that comes, maybe process 1 requires to be added, because there are some features that you need to add from process to process 1, you cannot add because it has already been accommodated in the what? In the memory. So for this case, you need the users to view the memories here. You need the users to view. So this one must be contiguous. So for you to undo that, you have now to allocate it, and you define a table. You must define a table. So for this case, I require a page frame table. And this is the page frame table that I'm talking about. So here we have the page frame. Here we have the page frame table. And this page frame table is one that will be used to allocate a process in the first core memory. So for this case, we can assume that we are having process 1, process 2, and process 3. But this process is supposed to allocate to frame number 4, frame number 2, and frame number 3. Remember, what is determining is the size. Remember, that is what we said about the memory allocation. We require size of the memory. Three. So in this case, can you see these two memory have not been used, and that's why we still require what you call compaction after allocating the memory. So we still require compaction, and that is why this is now what we can term as the hard disk, or maybe we can term this as the RAM that you are supposed to allocate here. And that's why if you look at this, we have already allocated a CPU. Then the CPU has a PD, which is a page number, where we have said a page number is used as an index into a page table, which contains base address of each page in the first memory. Then we have a page offset, which is supposed to now to allocate this to a frame in that. And that is why we have already allocated some pages to a first core memory. And when you allocate it to the first core memory, now it will become easier for us now to interpret the executions for that. So we can say, when you are using paging, it is much easier because you allocate pages for each allocation. So we are not having page 1 that is having many allocation in it. We are having page 1 with its own allocation. We are having page 2 with its own allocation. You're having page 3 with its own allocation. Do that. But what if now you don't have a big size for this allocation? And if you don't have a big size for this allocation, what will you have in that allocation? So that's why sometimes we need to work with other memory techniques. Now, those memory techniques that we are talking about, one of them is what you call the segmentation. So let's first of all understand this page table, of which I have already defined that. Is the data structure used by virtual memory system in computer operating system to store mapping. What I have done here, I have mapped. Process 2 is supposed to be somewhere here. That is mapping, allocation, where we are supposed to allocate. And virtual address, remember, the other name for virtual address we said is what? Somebody can answer that, please.
The other?
Another name for virtual address is what? Can you hear this? Can you hear this?
Can't hear you well.
Yes?
Pardon?
I'm asking, what is another name for virtual address? The one that I'm highlighting here.
There?
Can you see what I'm highlighting here? The one that I'm maximizing? Can you see this? Virtual address. Another name for virtual address is what? Are we in the same class?
Yeah, we are listening, but I'm not getting well.
Okay. You're not getting the question or what?
What you have asked.
Okay, I have said, I have asked a question. Another name for virtual address is what?
For another name for
virtual address. This one that I'm highlighting. Can you see? Can you see my notes?
I can see, but you're not indicating.
This one, virtual address. I'm talking about this, eh? This one, virtual address. Another name for virtual address is what? Can you see now? Can you see now? Yeah?
The diagram.
Which diagram can you see?
Yeah, I can see the diagram.
You can see the diagram. Now, I'm asking, let me try to redirect the question again. Eh? So what I'm asking is, we have talked about virtual addressing. Then yes. I'm asking a question. What is another name for virtual address? Another name for virtual address? This one that I'm highlighting here. Another name? Is it clear? Is the question clear? Amodi?
Yes.
Now, what's another name for virtual address? Another name for virtual address, and I think we have talked about it, is what you call the logical address. And when we talk about logical address, what are we talking about? Remember, we have said we have two addresses here. Logical address and physical address. And the moment we are talking about the physical address, we are talking about the hard disk or the primary memory. What about the logical address? When you talk about the logical address, which memory are we talking about? If you look at now the previous structure that we defined, can you recall this structure? There is a structure that we said, we have a structure. We said we can have the CPU. We can have the cache. We can have the primary memory. And we can have the secondary memory. So another name for CPU is what you call the virtual memory, or what you call the logical memory. And when you talk about the virtual memory, we cannot see the memories or the that are created in a memory in a CPU. We don't know the size that is created in a CPU, but we define that through the physical addressing. So we define that through physical addressing. That's why if you look at this diagram, because we cannot see, I think you can see that diagram. If you look at this diagram, we're starting from this CPU, where we have the logical addressing here. Then here we have the physical addressing. Because we cannot see what's within the CPU, now we require a physical address so that we can see what we are supposed to allocate in a page. That's why we are saying these are pages. So it's like a book. If you peruse your book, and maybe I'm trying to peruse the book that I have here. If you try to peruse a book, we already have different pages. And these different pages that we have, maybe we can have page 1, page 2, page 3, but it has its own sum page or framings. For these framings that we have, maybe you can say, let me go to page number 1 in line 15. So in that, it is the same as saying we are having a memory, but this memory that we are having, we are locating it in the physical memory. So we are moving from here, pages, we are located to the physical memory. So if you go inside a page, you'll be able to see what it's inside a page. Are we getting? Is that clear?
Yes.
Hope you are understanding what I'm saying. Now, that is why we are saying paging is more relevant in a time where now we are not using some context. Like now in partitioning, we had some issues, or we had some problems of allocation. And that's why we had some issues on fragmentation. But for this case, we don't have much of fragmentation. The fragmentation that we always have here is what you call the external fragmentation, which we said we cannot completely do away with it, but we can somehow reduce it. But the way we cannot always reduce it is by making sure that now we can use another method so that we can be able to reduce it completely, not completely, but slightly. We reduce it. And that's why we have said we need to use what? Segmentation. Now, let me ask a question. How many memory techniques do we have? How many memory techniques do we have? Friends, how many memory techniques do we have? Gomia. Are we in the same class, Gomia?
Yeah.
So can you name at least one memory technique?
Dynamic.
Okay, that is part of what you call partitioning, because if
Yes.
I can recall what we have said is that we have said we have partitioning,
Yes.
and partitioning is always classified into two. One is what?
And mapping.
Not mapping. There is no mapping on that. So what we have said, let me try to summarize that a bit. Let me use a PowerPoint to summarize that. And when I'm using a PowerPoint here, I want to be very brief. I will say types of memory techniques. Types of memory techniques. One, where we can say we have one. One, we have partitioning. Partitioning. And the moment we have partitioning, we can have what you call dynamic partitioning.
Oh, it is under the partitioning.
Yes, it is under partitioning, fixed partitioning. Okay. So in this fixed partitioning, we have said that we have what you call equal and equal. Are we together now? Yes. If you come back and then maybe you go to the second type, this is what we have said we have paging. Paging.
Yes.
And in this paging, we can maybe talk about what you call dynamic paging. Dynamic paging. And when you talk about dynamic paging, because it is a sub of paging, where in many cases we say that this uses what you call fixed allocation.
Fixed allocation.
It uses fixed allocation, but this one uses dynamic. And when you talk about dynamic allocation, what we have said, we allocate the process the moment it arrives. But for this one, we allocate it before it is like now we know the number of pages that we are supposed to have, but we don't know the number of pages that, the number of processes that we are supposed to have. It is like we know what you will get after this course. Maybe it's like you'll get a distinction, but maybe at the end, maybe you get another grade. So we are spectating on that. You're not supposed to spectate on that because now you don't know the size of a process. And for you to do this, in most of this paging, because it uses a trait of dynamism, that's why we can say the second part that we have is what you call segmentation as partition. But this segmentation is the one that is able to use what you call dynamic allocation. So this one uses dynamic allocation. But paging uses fixed allocation.
Fixed
We are
allocation.
saying it has reduced by, it has been improved, sorry, by using dynamic paging, or what you call, sometimes we call it demand paging. And the moment you talk about demand paging, this is when you say we allocate a process, we allocate a page when we know that a process is available. It's like now I cannot create a very big room and I don't know the number of students that will be in that class. So first of all, I know the number of students so that I can be able to create the class. So in this dynamism is where we say, either maybe I have it in this diagram, or maybe I don't. If I don't have it, I will be able to draw it. So when you're using dynamic paging, maybe I can draw that. Let me draw that. I still use paint. So we have new. Where we can say maybe we are having an allocation here, and then we are having a physical allocation here. So what we can do, some processes are moving to the logical addressing, and the other ones are moving to the physical addressing. So in this case, we can do what you call swapping. And if you can remember what we said about swapping in process management, it is when the memory is too small to accommodate everything. So you need to move it to an external storage so that you can wait for this memory to free itself, to free its execution. And now we start executing it. So for this case, if you have A, B, and C, D, here there is another one, maybe K, L, M, N, which is still waiting to be executed here. So the moment we are swapping, we are moving it from the physical to this, we are swapping in. But this one, we are swapping out the memory. So in this case, we can now say we are allocating a process because we know the availability of that memory. So for this case, if you look at now this, that's why we are saying it uses some dynamism, but it is an overall, it is like a fixed allocation. Because the moment you know the process that is supposed to be allocated there, we can still allocate. So the question that I was asking is, how many types of memory techniques? These are types of memory techniques that we have, but we have another one that we call the virtual memory. And the moment you talk about the virtual memory, because I have seen the diagram there, we can maybe explain with it. And before I want to explain segmentation, but in the virtual memory, it is where we are creating a hard disk. If the memory cannot accommodate everything, because we always use memory for execution. If it cannot be used for execution, if it cannot accommodate for execution, now we can take it to the secondary storage waiting to be executed. Instead of telling the user, okay, we don't have enough memory for that. And if you look at this, we have pages, memory map, then we have physical memory and the backing storage. So this backing storage that we have here, we can call it the secondary storage. We can call it the secondary storage. And that's why if you can look at this, we are saying the advantage behind that, large program can be written as virtual space available is huge accompanying the physical memory. So it's like now we are accommodating a process of 2 GB, but the process of 2 GB cannot be fully accommodated in the memory because the memory is full. What can you do? Just take it to the secondary storage so that now users can bring other processes. We will not halt the user's execution. We will not tell the users, okay, can you hold on? Because now the process cannot be executed because we have you don't have enough memory. So for this case, we will be able to explain as we complete this. So if we can recall what I was saying, in paging, we are trying to create fixed allocation. And because we are trying to create fixed allocations, we require virtual addressing, and we still require the physical addressing.
Physical address.
I have explained this with this diagram, where we have said, first of all, you have the logical addressing, then we have the physical addressing. Then we try to map them. So mapping is not a method. Mapping is a process of allocating is a process of allocating some activities or processes in the physical memory. It's like now I tell you, can you try to bring this item from A to B? Then you tell me whether A is connected to B or C is connected to A. So that is what we are calling mapping. But now we want to try to create what you call expandability. And the moment I'm trying to create some expandability within the execution, because expandability is, in another term, we call it scalability. So we need to look at now what we call scalability in the process execution. And for you to create this scalability, that's why we use what you call segmentation. Segmentation. And the moment we are using segmentation, we are now creating segments for executions. And I want to explain this through the use of paint. So we have a frame, but this frame has segment. Remember, always a memory starts from segment 0. Then we have 1, we have 2, then we have 3. So for this segment, we are saying, 1, we are allowing what you call efficiency. We are allowing efficiency, and we are allowing what you call scalability. Because if this segment 0 is supposed to store process 1, so we have to store this process 1 through the use of what you call modules. So process 1 has its own module. If you have process 2, it has its own modules. And what can you do on this? So if you know that this segment is enough to hold the process 1 and process 2, we can still accommodate. But if you look at paging, we only allocating one process at a time in a page. But for this one, it has more processes in allocation. That is the advantage. It still allows the users to re-amend the executions. Remember that now, if process 1 has already been accommodated in segment 0, and is still required to add something on process 1, we can still add this process again. It allows that addition. And that's why now scalability comes in. Efficiency is because now we are not losing anything. We are not losing any content within the execution. And for this case, because now we still require the physical allocation somewhere here, we now require what you call the segment table. We require the segment table. Where the segment table, it has the segment number, and then it has what you call the size. So the size defines how this physical memory is supposed to be allocated. Because this memory is not allocated before the execution, it is allocated during execution. So this is what you call late binding. So we are using what you call late binding. But the others, we are using what you call the early binding. So for this case, if now it is segment 0, it has a size of 400. And this size is supposed maybe to start 100, 200. It is starting from 0 up to the maximum size that is given to this storage. So 200, 300, 400. So you can allocate segment 0 here. Now, this is what we are saying. It is what you call mapping. If you have another one, which is 200, now this one, you can map here in allocation. So this, the whole of this is what you call what? Mapping. Now, if you can go back to these notes, we are saying we are having a segment. It's a technique to break memory into logical pieces. These are logical pieces. Those are logical pieces. And these logical pieces, where each piece represents a group of written information. So if you look at this piece, if we know that this process 2 is related to this, so we are storing the same family, the family in a process. That's why we are saying if process 1 has to be added, we can still add because now we are storing the same family of process. group of related, for example, data segment or code segment for each process, data segment for operating system, and so on. So this diagram that I have drawn here create a good interpretation of what we are supposed to have. So if you now, somebody asks a question, maybe explain what is segmentation through the use of a diagram. So what I expect you to do, I expect you to come up with what you call logical segment table. You come up with what you call segments. Segment, maybe we can have segment 1, segment 0, segment 1, 0, 1, 2, 3, where we have said we can stop process 1 here, process 2 here, maybe we can stop process 3 here, process 4 here, etc. Then here, I require what you call the segment table. And this segment table, it should have what you call the segment number, and it should have what? The size. Where now you can allocate the 0, 1, etc. Then after that, we can have the physical memory. And in this physical memory, if this one is supposed to be, this is 0, segment 0, 1, 2. So this is where we have 0. It has a size of 200. This has a size of 100. So in this case, now we can provide sizes. This is 100, 100, 200, maybe 300, and then we can map. This one you can map. If you have another one which has 400, and then here we have 400, so this one we can map here. That is a very simple interpretation of what we are supposed to get within the segmentation. Now, if you look at this, automatically we have reduced completely what you call external, and we have reduced the what? The internal fragmentations. Are we together?
Yes.
Is there any question up to that point? So that now we can continue, maybe with the presentation. So I will send these notes. I will still add those notes to you, to your portal, so that we can have. So that's why we find that now here we have to ask ourselves here. There is a question that we have to ask ourselves here. Is the size equal to what we want to have? If it is not equal to what we want to have, now we can do away with that allocation. Is there any question? Just let's have 2 minutes for us to ask questions on this. Come on, Pete, and Gomia.
Pardon.
Is there any question that you can ask?
So what is the importance of the segmentation table?
The importance of segmentation table that we have defined here is to allow us to allocate the processes in the physical memory. So it is giving us the green light of how we are supposed to allocate the physical memory. Because we have said we cannot allocate the physical memory before we know the size that is supposed to be allocated to each and every segment.
Yes.
So it is assisting us.
It depends with the size.
It depends with the size. That's why we have already defined some sizes here.
Yeah.
It depends with the size. And why are we depending with the size? One, we want to reduce these internal and external fragmentations that we have.
Segmentation.
So that now we don't have loss of content. Remember, when we are looking at partitioning, we are moving back to relocate the process where it was allocated. When you are using the other one, we are still relocating the process. But here now, we can use the index in the same allocation. Is it clear?
Yes.
Is there any question?
So it says the backing storage is the same as secondary storage.
Yes, backing storage is the secondary storage. Because if you look at the backing storage, it is mostly used to store either permanently, we can store it permanently or temporarily. And if I can use the diagram here, what we have said
like
is
the internal segmentation. Yeah.
No, it is not like internal segmentation. What we are saying is that when you are trying to execute some processes, and I think you have ever worked with your mobile phone, sometimes it tells you we don't have enough memory. See,
Yeah.
So if your mobile phone is telling you we don't have enough memory, it has already looked at the external memory. And this external memory that it has looked at is either the flash memory or maybe the mem card that we have. And if you don't have the mem card, now automatically that's why it tells you that you need some card. So that's why if you look at an operating system, we create the backing storage. And this backing storage, it is like a handy disk. It is like a handy disk. It is a handy disk, which is virtually. That's why when you're installing an operating system, automatically it creates a virtual memory. And this virtual memory, it should be 2 times the normal memory. If your memory is 2 memories, or 2 GB, if I can use that as an example, in the backing storage, we have 4 GB. So the moment you are trying to execute a job, and you find that the memory that you are using is too small to accommodate your process, automatically it is switched to the backing storage. And when it is switched to the backing storage, it means that now we can store it temporarily, so that now the memory that was used to execute jobs, it can first of all free for that execution. Because this secondary storage is not used for execution. It is used for storage. Are we getting that now?
Yeah.
Hope you are getting?
Yes.
Yes.
Yeah, we get.
Another question?
No.
Yes. Am I talking to Amon or Gomia?
You are talking to Gomia.
Gomia, okay. Can you ask Gomia, please?
I don't have another question.
Oh, okay. Omondi, do you have another question?
No.
Okay. I think you have understood that. So that's why we are saying, if you are using segmentation, at least we are trying to solve some issues in the memory, and we want to totally reduce completely the memory, the issues that we had within the memory. So I have talked about the virtual memory, and the virtual memory that I have talked about is something that you cannot see. And so if maybe on the background, you can mute your microphone. You can mute your microphone. Just mute your microphone. Yeah. Just listen. If there is a noise in your background, please. So if you look at now the virtual memory, we are saying this is the memory that has been created in a secondary storage. And it has been created in a secondary storage to assist mostly the users to accommodate the processes that were not accommodated in the main memory. Remember, we use RAM, we use the primary memory to execute. But if the memory is not enough for the execution, where can we store them? We store them in a virtual memory. That's why I was saying, when you're trying to install an operating system, we have to install the operating system, and automatically it creates a virtual memory, which is 2 times the normal memory. If your memory is 2 GB, automatically it has to multiply that with 2. So that now we can be able to create more space in that allocation. That's why we are saying it's a technique that allows the execution of processes which are not completely available in the memory. Which are not completely available in the what? In the memory. Meaning, the memory was not able to hold those processes, and that's why we have already allocated the secondary memory so that we can at least store it temporarily, awaiting the memory to be free so that we can use it. And that's why in most cases, when you're using the operating system, it has to use that. And if you look at that, that's why I was talking about backing storage, and this is the same backing storage that I have talked about. If you look at the advantage for that, you're saying more physical memory are available as program, so they occupy very less space on actual physical memory. it is a very small portion within the secondary storage, which can be used in that allocation, or which can be used to allocate those processes. But sometimes you ask yourself, if now we are having a very small hard disk, and this hard disk cannot accommodate all the processes that we have, so automatically it tells you your memory is not enough. When that computer tells you the memory is not enough, it is because now the processes that are supposed to be executed, they cannot be able to accommodate the memory. Then you find that even your computer halts. It keeps on halting. Your computer is too slow to run the processes because the virtual memory that we are having has some issues on the execution. So you have to look at that execution and be able to understand that virtual memory is very important in the execution. And I hope maybe we can be able to understand the executions that you are having on it. So we have to look at now the execution of these memories, and you're trying to speed up the execution. That is the first thing. We are trying to improve the memory utilizations, and we are trying to make sure that now we have faster execution and less output manipulation or usage or requirements. So if you look at most of the executions, they use what you call virtual memory, and they use what you call segmentation, depending on the operating system that you are using. So if some cases you are using what you call Linux operating system. So, and most of the versions that we have, like now, if you have the Linux operating system, you can use what you call Red Hat. You can use what you call the Fedora, and maybe we can use what you call the Ubuntu. These are the operating systems that mostly work with virtualization, or this is what you call the virtual memory, and they use what you call demand paging for the right executions. So that is what we need to understand about this virtual memory. And I have given out the advantages for that. I still send those notes to you so that you can familiarize yourself. And if there is any question, maybe you can ask, and I can still repeat. Even this script, you can listen after this. I will set it to be listened afterwards, which will be on your portal. The next one that I was talking about is what you call demand paging. And I think what we have said about demand paging, we allocate the process the moment we require it. And I think I had explained that the moment we are using what you call swapping, if the diagram is still there, no? So we were using swapping in and swapping out. So when you are swapping in, we were saying we were moving it from the physical memory to the main memory. So the main memory is now the memory that we are using for the execution. Yes? Are we together?
Yeah.
Okay, what I'm saying is that
Yes.
if you can remember the diagram that we had on demand paging, we were saying we can have some processes, but the moment we require them, that is the time that we load them in the physical memory, in the main memory for execution. And that's why we have two things here, swapping out and swapping what? Swapping in. Because we can remove the process from the main memory to the physical memory, and then from the physical memory to the main memory for execution. So for this case, when you are doing this, it always results to what you call the page fault traps. And page fault traps, I will be able to explain that when we will be looking at algorithms for the memory management, because when you look at the memory fault traps, then we have what you call the memory hits. And memory hits are mostly used when the memory that was supposed to be utilized was utilized previously, and we are utilizing the same page in that memory. Then the memory fault, it's when you find that that memory was not utilized before. So you are utilizing it for the first time. And in that case, we can say we have the page fault traps. So which we find here in this what you are calling the demand paging. And this diagram clearly indicates that now we should be able to allow large memory or large virtual memory. And that's why we say that for you to use demand paging, we require large virtual memory, more efficient use of the memory, and unconstrained multiprogramming. So when you say unconstrained multiprogramming, mostly we are saying we don't have some hindrance in the execution. It is when we allocate a page, we know how the page has already been allocated, where we don't have any hindrance, meaning there is no limit of programming. We can still reprogram and reprogram and reprogram again without loss of that content. But there are some disadvantages for that, which you can still be able to look at. Maybe as I said, those notes, because we look at now, due to lack of implicit constraint of job boundary space size. Sometimes we can have a very large process, but this large process, we don't have large memory. So in this case, we have now to look at how we can be able to store that process without loss of that content. And that's why maybe other memories comes in, which we call the registers. The registers comes in so that we can be able to allow that allocations for the processes that we are having. So what I can say is that maybe for today we can stop at that point. Let's try to ask some questions before we terminate this, and then we go to the chat room. We share some things that we are supposed to share. I will go to chat room, or we need to go to the chat room, which I will create after this, which we can share some things and be able to maybe try to brainstorm on what we have understood. Then after that, we will go to the next part of the explanation, which we call the page replacement algorithm. And I don't want to start this because we need to have some diagrams. And if you can look at this, there are these diagrams. I need to explain how they are used within the executions. So we might be able to look at them. So please, for now, let us ask questions. And maybe if there is a burning issue, you can raise. If there is a problem of hearing, maybe we can still raise on it. Mr. Karani.
Yes.
Mr. Karani, you're not too late. And what was the issue? Was there an issue? Because you are
About
very
what?
Huh? Pardon?
The issues about?
I had only 2 students, but now you have joined. Was there any issue before?
Yes, some technical issues. Yeah.
Oh, okay. Don't worry,
Yeah,
those are
that's
allowed. But, next time it will be okay. But
Yeah,
I will
it's
send
okay.
this clip to your portal. You can still
Okay.
listen it again and again because it
Okay.
is recorded. Yeah. So what I can say is that we need to raise some issues that you have not understood. If you have understood, maybe we can say we proceed to the chat room. Any question?
Okay.
Any clarification?
No question. Have no question.
Who is that, please? When you is it Omodi or Ngomia? Okay. Is there any question?
No question.
No.
Okay. Can you link to chat room, please? And maybe I can try to give you an overview of these algorithms. If you look at the algorithms that we discuss, there are very few, but don't confuse these algorithms with process management. Please don't confuse them with process management because they are totally different. The way we operate them, they are totally different. But you can see first in, first out is always used. But here we have added an optimal page algorithm. If you can see, there is recently used algorithm. So I will explain next time on how we can operate with them. Then after that, we have least frequently used algorithms, most frequently used algorithms in that. And after we explain that, we will be able to understand why we need to use these algorithms and how we can use them in the memory allocation. So for now, maybe we can end this session at this point, and then maybe we meet in the chat room. Is it okay?
Okay.
Can you meet in the chat room?
It's okay.
So for those people who don't know how to use Wiki, there is a platform that is called Wikis. So I can post some definition there. Then you challenge them. So you are supposed to challenge them. You add them. It is like now you are adding a content on that. So if I use Wiki, you can challenge that, or you can maybe try to edit whatever I have written. So let us meet in the next session. Thank you.
Bye.